Okay, for objective 7.1c, our topic for today is using dimensional analysis when we study circular motion. So it's going to take a couple days. Be patient. But you will be successful when you can use a dimensional analysis to convert a given measure over time into a desired measure over time. And we'll explain what that looks like by doing multiple examples when you're working on your practice. Okay, and I will define what is dimensional analysis. We'll talk a little bit about angular speed and linear speed. There's a place for vocabulary there at the top of your notes. You don't need to put anything in that section, okay? All right, so let's start with the two formulas. If you choose, if this is how you work and you want formulas, I'm going to provide them to you, okay? But they're not, you don't have to use them to do the math. Let me ask you a question real quick. You guys are familiar with getting in a car and driving to San Diego, right? And the distance that you're going to San Diego will be equal to the rate you travel times the time that you're in the car. So now I would like to be finding speed. So if I know I have to go 180 miles and it's going to take me 3 hours to get there, how could I determine my speed? Yeah, rate is equal to distance over time. So rate is speed. Distance is how far do you go from beginning to end, and time, of course, is your measurement in time. So change in distance over change in time gives you your speed. It's the same in angular speed. But you're doing a measurement in radians. How many radians are you turning? So angular speed, which is denoted by the omega sign, so that's angular speed right there, is equal to your change in theta radians. Okay, so how many radians did you change? How many radians did you spin? Because we're going in a circle. We're stuck on this circular path. Divided by the change in time. That's how you find your angular speed. It's just change in distance, but our distance is being measured in angle, degrees or radians, over your change in time. Linear speed in a circular motion will be denoted by a V, and linear speed is equal to your change in arc length, which has to do with your circumference and your radius, over your change in time. All three formulas that I've just discussed here are a measure in distance over a measure in time. It's just in angular speed, you're measuring your distance in radians or degrees. Yes?
Can we do this in math analysis?
We may have. Okay, now angular speed does not require radius. Okay, does not. Linear speed does require or radius. Or you could also use the diameter, but you can find the radius from the diameter. So anytime you read any problems today and the diameter is mentioned or the radius is mentioned, make sure you record that value and you use it when you're trying to find your linear speed. Got it? And one other statement that I'd like to make for both of those is this. Remember this. 2 pi is equal to 1 revolution. And I meant to write equals. But that's 2 pi radians is the same thing as 1 revolution. Okay, and we use that when we're looking for theta. Okay, that'll help us find our change. That's our change in angular degree if we go around one time. 1 revolution is 2 pi radians. And not, you don't have to put an S on it, just 2 pi rad. Linear speed, 2 pi times the radius is the same as 1 revolution. Okay? So when you're looking for angular speed, 2 pi rad over 1 rev, because we're going to use a dimensional analysis, will be very helpful, because that's knowledge that you should know, right? If I say, well, I'm going to do 1 revolution, how many theta? What's theta? 2 pi radians, right? If I say we're going to do 1 revolution, what's your circumference? 2 pi times your radius, okay? One measures your change in degrees or radians, and one measures your change in feet or inches or whatever your linear path around your circle is. All right? So now let's just explain dimensional analysis. Dimensions are just measurements, okay? Length in inches, width in inches, etc. Just a measurement, okay? Different dimensions. And if you want to use a dimensional analysis to solve a problem and do a conversion, all you have to do is say, okay, what do I know? What can I easily access in my brain? What conversions do I know? And what do I desire to know? So let's take a look at this problem. It says, how many seconds are in a year? I can't easily access that information in my mind, but I can do a dimensional analysis by accessing how many seconds are in a minute. I know that, and I can convert that to how many seconds in a year. So here's what I desire to know. How many seconds are in a year? So that would be my label of my final answer. I want to know that. How many seconds are in a year? That's my desired outcome. I'm going to start with the information that I can easily access. There are 60 seconds in 1 minute. True statement. Okay? Now, I have seconds in my numerator, if you notice, and over here in my desired outcome, I have seconds in my numerator. So I don't want to cancel that unit out. I want to keep that dimensional unit in my problem. But I don't want minutes in my denominator. I want years in my denominator. So what I'm going to do now is get rid of minutes. To get rid of minutes, I need to be able to cross-simplify or cross-cancel them. So let's go now to we're trying to get from minutes to years. What do you know? There's 60 minutes and 1 hour. You got it. Okay, so this allows me to go like this. Okay, I got rid of that dimensional, that unit of measure. I don't want that. But I also don't desire hours. So what would I do now? I want to get rid of hours. What do I know that I can easily access? 24 hours in 1 day. All right, so that allows me to go, okay, so no hours. I'm going to use a different color here. Hours are gone. So now I have seconds per day. I don't want that. Last conversion. I don't want days. 365 days in 1 year. This allows me to say, all right, days are gone. And all I have to do now is plug all that information into my calculator. And I don't really need to divide it by 1, right? So 60 seconds times 60 minutes, 3,600. You guys are going to have to help me out. I know it's 31 million something. But like I said, I can't easily access it. I can't remember it, and I've been doing this problem all day. What is it? 31,104. I don't think it's 104. Are you sure? 536. 31,536,000 seconds per year. There it is. So that's an explanation of dimensional analysis. You're accessing what you're given or what you know, and you're converting it to what you desire to know or what you're being asked to find. Now, here's what I want to explain to you. As I'm multiplying all of these values that I started to choose, all I was doing was multiplying my beginning statement by 1, because 60 minutes divided by 1 hour, that's 1, right? 24 hours divided by 1 day, they're the same thing, 1. 365 days to 1 year, that's 1. It's always multiplying times 1, sometimes some form of 1. So not really changing the value, I'm just changing the units of measure, dimensional analysis. So let's do some practice that has to do with circles. So I'll give you a moment to copy this problem down. All right, so you've got this problem copied down, and so you have a circular blade, and I'm talking about a saw blade, so it's got little teeth on it, with a 12-inch diameter. Oh, we've been given diameter, so we should immediately identify what? The radius of 6 inches. That's helpful. 2 pi radius when we're finding angular speed. Also, we can do pi times diameter, but it's good to have radius. Okay, so a circular blade with a 12-inch diameter spins at a rate of 1800 RPM. When you see RPM or RPS or RPH, God bless you, you are being told things in revolutions. How many times does it complete a revolution? Okay. What is the angular speed of the blade? So how many degree changes per minute? So we're starting with our starting value. We were given 1800 revolutions in 1 minute. And I'm going to use, definitely going to use a dimensional analysis. I can use it over and over and over again. That's what I'm given. My desired outcome is what? What do I want? What are my dimensions? Radians per minute. Okay, so that's my desired outcome. So I want to convert 1800 revs per minute into radians per minute. So let's readily access what we know. Here's what we don't want in our final answer: revolutions. I don't want revs in my numerator. I want rads in my numerator. So here's what I know. 1 rev equals how many rads? 2 pi rads. Absolutely. 2 pi radians. I think I'm done with what I need. I can cancel revs, and what I have left in my numerator is rads, and I have minute in the denominator. So that gives me, if I plug that into my calculator, 3600 pi radians per minute. I would like you to convert that to 2 decimal places, please. And I think I have 11,309.73 radians per minute. So that was just a one conversion, right? Just remember, you start with what you want. You use that, you access that information that's readily available that you know about, and then you just keep using all the information you know until you get what you want. Now let's look at B. B says, find the linear speed of a tooth that's on the edge of the blade. So that's at the end of the diameter, right? Okay, or at the end of the radius. But we want it in feet per hour. So our desired outcome is feet per hour. This is what we want our final dimensions to be measured in, feet per hour. So we start with what we know. What do we know? That there are 1800 revs in 1 minute. And we need to convert that to linear speed. How many feet per hour is that tooth having to travel? It keeps going in that circular motion, right? But it's traveling inches, right? And we're doing math in inches here. So I don't want revs. So I want to get rid of revolutions. I don't want that. So readily available. What do you know 1 rev is in relationship to the distance around the circle, which helps us find our linear speed? 2 pi. No, because I don't want it in radians. I want it in feet. Linear speed. times 6 inches. That's the circumference. That's how far the tooth has to travel. Remember, when you're looking for linear speed, the radius is important. Okay? That's readily available. We know that. The circumference around one revolution, right? One revolution is one circumference. Okay, so here's what I've done so far. Revs are gone. So now my answer is going to be in inches per minute, but I don't want that. I want feet per hour. So I have to access more information that I readily know so that I can convert this. So let's get rid of minutes first. I don't want minutes, I want hours. How do I get rid of minutes? That's right, 60 minutes in my numerator, so I can cross simplify my minutes in 1 hour. Okay, so that allows me to go, all right, I'm going to grab up a different color here. I can cross simplify across multiplication anywhere I want. Remember, multiplication's commutative. I can multiply in any order that I want. Okay, so now I have inches per hour. I don't want that. I want feet per hour. Readily accessible information that you know. I want inches gone, so I got to put it in the denominator. What do I know about inches in relation to feet? 12 inches in, 1 foot. Okay, so I have my desired outcome. I have feet left in, oh, let's do some more cross simplification here. Let me grab another color. So the inches, I can cross simplify that. So now what I have left is a dimension in my numerator is feet and in my denominator is hours. So there we go. All we want to do is multiply all of that out and divide by 12. Here's what I do. I plug it into my calculator. I push my fraction button and I just start typing it in. 1800 times 2 pi times 6 times 60 over 12 and hit enter so that I don't have to do multiple entries into my calculator. Just type it in as one long fraction. What do we get? I know you get a number. I need it. You're plugging it in. 108,000 pi? 108,000 pi feet per hour. Well, we don't usually measure linear speed in pi, right? So let's convert that. Hit your conversion button. 339,292.01 feet per hour. Okay? And so you'll be doing many problems like this where you're going to have to start with your given information, whatever you're starting with, and then you have to think, do I want radian? Am I measuring angular speed, 2 pi radians over 1 rev, or am I measuring linear speed, 2 pi radius over 1 rev? Make sure you're always labeling every value you plug in, okay? And then you're using your readily available knowledge to convert from whatever measure over time you're given to whatever measure over time that is desired, okay?